Let us look at some of the basics of a cube. A cube has 6 faces, 12 edges, and 8 vertices. So does a cuboid. The only difference between a cube and a cuboid is that in a cube, all sides are equal, while in a cuboid, the length, breadth, and height may vary. Before you move on, you should ensure that you understand how we are getting these 6 faces or the 12 edges or the 8 vertices. It's very important for any solid object, while doing questions on any solid object, that you understand the basic shape of that object. Even if we do not do any of the formulas that we'll do later on, but you understand the shape, you should be able to handle the questions. On the other hand, if you have done many questions on that topic, but you do not understand the shape as well, you might still struggle in the examination. So please ensure, just maybe spend 5 minutes looking at a dice or a book in case you're not comfortable how we are getting those 6 faces or those 8 vertices, etc. One more thing before we move on. So for solid objects, there is this formula which might be useful, although it's not very important from a CAT perspective, but still something to have at the back of your mind. So what this states is that the number of faces plus number of vertices, if you take away the number of edges for any solid shape, you'll get 2 as the remainder. We can just check for a pyramid, let's say. So in a pyramid, there are 4 faces and there are 5 vertices. So this tells me that the number of edges in a pyramid would be 7. You can count to check. Again, it's not very important from a CAT perspective, but just something that you should know. Let's move on to the next topic. There are many questions which comprise cutting a cube into various pieces, and they'll ask you the number of pieces, or they'll cut and remove a certain part, and then there'll be questions made on the back of it. So we'll just have a look at how that works. On the left hand side of your screen, you can see that a cube has been sliced into 2 parts. So one cut has been made, and that has resulted in 2 parts, right? While on the right hand side, if you can see, on the right hand side, we have horizontally made 4 cuts, and those 4 cuts have resulted in 5 pieces. So 4 cuts have resulted in 4 plus 1, 5 pieces. Now that gives us a way to count the number of pieces that will be formed if you make n number of cuts all in one plane, because all these cuts are in the same plane. All the horizontal cuts are in the same plane. So if you make L number of cuts, if I make L number of cuts in one plane, I'll get L plus 1 as the number of pieces. However, if I make another cut which is perpendicular to this plane, so let's say in the rightmost graph, I am making one more cut which is more vertical in nature. So I make this cut, excuse me for my drawing, so now I have cut it this way, and now I already had 5 pieces, but now I have 6, 7, 8, 9, 10. So all the earlier 5 pieces have been divided into 2. So you see, just by one cut, I have been able to double the number of pieces. And that takes us to our formula for the number of pieces if we are cutting across planes. So if you are cutting across length, breadth, and height, the number of pieces that you will get will be L plus 1 into B plus 1 into H plus 1. This is a useful formula to know, and there are various questions made on the back of it, some of which we'll do very shortly. The way to use this would be, if somebody tells me that there were 7 cuts made lengthwise and 3 cuts made height-wise on a cube, how many pieces do you expect to have? Then that becomes 7 plus 1 into 3 plus 1, and that is 8 into 4 equal to 32. So I'll get 32 pieces that way. We'll quickly look at how questions are answered using this formula. Let's look at the first question. What is the maximum number of pieces I can get by making 6 cuts in a cube? So if you remember the previous formula, it becomes, what we have here is that we need to maximize this number. L plus 1 into B plus 1 into H plus 1, and we need to get the max of this number. What we have been given is that the number of cuts that we can make, that is L plus B plus H, is equal to 6. So we are allowed to cut across planes, but the maximum number of cuts that we can make is 6. Now, if you have done your maxima and minima properly, this should jump out to you straight away. This is a case of finding the maxima of a function by using am greater than gm. You have been given the arithmetic mean of L, B, and H as constant, which is equal to 2. You need to maximize the geometric mean of the function, and if you remember that, it will happen when L is equal to B equal to H, which will be 2 in this case. And for that case, the number of pieces would be L plus 1 into B plus 1 into H plus 1, which will be equal to 3 cube or 27. So 27 pieces. So this draws on your knowledge of maxima and minima. If you're not sure how this is working, maybe you should go ahead and revise that part of quant. Let's look at the next question, which is fairly similar. A cube has to be cut into 210 pieces. So here we know the number of pieces that have to be constructed. L plus 1, we have been given this number equal to 210. But we are asked to minimize the number of cuts. So we have been asked to minimize L plus B plus H. Again, you can draw on the same information that was there earlier. This time your geometric mean is constant, but you need to minimize your arithmetic mean, which would again happen when L is equal to B is equal to H. But that would not happen here. And that is because when you put all three equal, in this case, you will not come up with an integer number. You will come up with a fraction, a decimal number. And that's not possible because the number of cuts cannot be a fraction. So you'll have to find the minima for L, B and H as natural numbers or at least whole numbers. It's again a maxima minima question. It has nothing to do with cubes. But if you write it into its factors and then see which number satisfy it properly, you'll get that 5, 6 and 7 are the values which satisfy this equation in the best possible manner. And the total number of cuts that will be needed would be 18. I'm not going into a lot of detail again because this is drawing into existing concepts which you would have read earlier. There are various questions where you would be asked how many parts of the cube have two faces colored in one color, or how many have no faces colored, and these kind of questions. So we'll have a quick look at how to approach those questions. We'll do some of them in more detail in later videos, but this is just to give a flavor of how that happens and to introduce some of the basics. So if you look at a cube, you'll notice that only the vertices have their three faces exposed. If you look at the boxes which are marked in blue right now on your screen, these are the boxes which have their three faces outside, exposed to outside, and if painted, this will be the one which will be painted. The yellow ones, which are on the edges and excluding the vertices, they have two faces exposed. So if I were to paint the entire cube, I'll be able to paint two faces of those cubes. And the white one, which are caught in the center of each face, which is ignoring the boundaries, they have only one face exposed. So these guys will only get one face painted if I were to paint the cube from the outside. There are cubes trapped inside for whom there is no face exposed, and those will be the cubes which will be discovered if you remove one layer from each of the sides. So how do you count the number of such cubes? Let's do this for a 4x4 cube for now, and then we'll go ahead and generalize it to an n cross n cube. Number of cubes with three faces visible, that's the number of vertices. So we have 8 vertices, so this number becomes 8. How many cubes have two faces visible? That's the number of edges, which is 12, into, for each edge you need to remove the two vertices. So we have 4 boxes on each edge and we remove the two vertices, and this gives us the number of cubes with two faces visible. How many cubes have only one face visible? You take each face, which is 6, the number of faces, and on each face you remove the boundaries. So I'll remove 2 boundaries for each length and breadth, and I'll square. So this becomes the number of cubes with one face visible. And then how many cubes have no face visible? That would be, I'll need to remove one layer from each of the dimensions to get to the inner layer. So what I'll do is, if I remove so for in this case it would be 4. So I'll start. If I remove the top layer and the bottom layer from each of the 3 sides and then cube that gives me the number of cubes which are trapped inside, which in this case will be 2 cube or 8. If you want to generalize it for an n cross n cube, what will happen is, how many cubes have 3 sets visible? They're equal to number of vertices, which remains constant. So we still have 8 here. How many cubes will have 2 faces visible? That will be each of the edge, and we'll have to remove the 2 at the edge, 2 cubes at the edge. How many cubes will have only one face visible? The 6 faces, and you remove the 2 on the side to remove the edges, and you square, and that gives you the number of. And then how many cubes have no face visible, as in are trapped inside? You need to remove 2 from each of the, you need to remove all the layers, which will be n minus 2 cube. So this becomes a generic formula. If you want, you can learn the formula. If you have seen the derivation and understood the derivation, you don't even need to learn it. You can derive it on the fly. So feel free to take a call on how you want to go about it. In the next class, we'll do some permutation and combination related questions for coloring cubes. And then in the third class, we'll take some questions which will also use some concepts we have taught today. See you on the other side.